Many designers are very comfortable with water pump selection. Fuel pumps are just like water pumps, except they contain a much more dangerous and flammable liquid. Selecting the correct fuel transfer pump is an important part of ensuring the safety of the building. We will take you through some of the basics on fuel system selection.
The pumps commonly used for fuel transfer are submersible turbine, centrifugal, or positive displacement gear pumps. Submersible pumps are widely used for gasoline service stations and also for diesel power systems. They have a low cost relative to their high flow rate and avoid the suction piping and priming problems associated with other pumps. Centrifugal pumps are typically used in generator applications from transferring fuel from delivery trucks to fuel storage tanks. They may also be used from transferring from storage to point of use, if they can be installed in a flooded suction condition. Otherwise, the limited suction side capabilities made positive displacement pumps a better choice. Positive displacement pumps have very good suction characteristics, a wide range of defined flow rates, and high pressure capability. Where lower flow rates, 3 to 30 GPM, are desired, then positive displacement pumps are preferred over higher flow submersibles. For high-rise building construction, the higher pressure capability of a positive displacement pump, up to 500 psi, is preferred versus a submersible, which is typically limited to 50 psi. The recommended flow rate for the pump is total fuel consumption at full load times the duty factor. Typically, each pump should be capable of providing the full requirement. A recommended duty cycle factor would be 1.5, so that at full load the pump is operating at 67% capacity. The duty cycle allows for the supply of the fuel to multiple units simultaneously without reducing supply to the furthest unit from the pump location. A flow capacity example would be 3 generators at 3 GPM consumption. At full load would be 9 GPM required times 1.5 duty cycle factor, which equals 13.5 GPM capacity. A special case for generator calculations would be where the generator returns fuel not to its day tank, but back to the bulk tank for fuel cooling. Since generator consumes only a third of its actual flow, the calculation for pump sizing increases by a factor of 3. So in our example, 13.5 GPM would become 40.5 GPM, a substantial difference. The required discharge pressure for the pump for generator applications is typically calculated as follows. Use 15 psi as the minimum inlet pressure at the day tank inlet solenoid valve. Then add 10 psi to allow for head loss in the piping, and the elevation static head of roughly 5 psi for 10 feet elevation. Then make sure you size the piping for maximum 10 psi head loss at the rated flow. A pressure example would be 15 psi minimum inlet, plus 10 psi pipe losses, plus 50 psi for 100 feet of vertical elevation, which is approximately 8 stories, for a total of 75 psi. For boiler applications, the calculation would be similar with the addition of pressure safety factor. The recommended boiler inlet pressure needs to be checked, since this may vary up to 100 psi. Then add 10 psi pipe loss and the elevation head loss. This will give you the required pressure at the boiler. We would recommend a 1.25 factor applied to this pressure to allow for inaccuracies in the back pressure regulating valves that are commonly used in these systems. For example, a boiler with a 50 psi inlet pressure requirement plus 10 psi pipe loss plus 50 psi elevation for approximately 8 stories would be a 110 psi required times 1.25 safety factor for a specified pressure of 137.5 psi. Some boiler and water heater equipment may require a very low inlet pressure in the range of, say, 3 to 5 psi. This can be very difficult to control with pressure regulators. So typically a head tank is used. The fuel supply pipe to the boiler room may operate at 15 to 25 psi. Then a regulator is used at the inlet of the head tank to reduce that pressure to about 5 psi. Then the fuel gravity overflows from the top of the head tank, back to the main fuel tank to provide a static head of 3 to 5 psi for the boiler or heater. Inlet and outlet gauges allow visual monitoring and troubleshooting for pump performance. These are typically liquid-filled and may include isolation valves. Ball valves are typically provided at the inlet and outlet of each pump to provide isolation for maintenance. An internal relief valve is provided to assure that the pump pressure will not exceed the motor capability, and also to provide gross pressure regulation for the pump discharge. Strainers are provided for each pump to prevent pipeline debris from damaging the internal components of the pump. The strainers are provided with cleanout ports. Outlet check valves. Check valves are provided at the outlet of each pump to prevent backflow through the inactive pump in a duplex set. Where pump mounting is such that pump vibration could be transferred to the piping system, then vibration isolators should be provided for the pump inlet and outlet. Specifying the voltage requirements for a pump includes voltage, phase, and horsepower. Submersible pumps are commonly available from 1/3 to 5 horsepower. 208 VAC single phase is most common for pumps less than 1 horsepower, and 480 VAC 3-phase is an option for larger submersible pumps. Positive displacement pumps are available in a full range of voltages and horsepower, commonly from 1/4 to 10 horsepower. Voltages may be 120 VAC single phase, 208 VAC single phase, 240 VAC 3-phase, or 480 VAC 3-phase. Selection of the motor horsepower is based on the flow rate and pressure required at the pump. Voltage selection is typically a consideration of the overall power distribution within the facility and, in particular, the availability of emergency power circuits. Motor starters are required for pump motors to comply with electrical safety codes. These characteristics would include overload protection and a means of disconnect. In addition, motor starters may have current sensors for proof of motor operation, hand-off auto switches for local control, and not-in auto monitoring of the mode selector switch. For mission-critical applications, it is important that the motor starter be operable in the manual mode, independent of whether or not control power is available from an outside source.